Welcome to Mystic Sci-Fi YouTube channel. Subscribe to get more such videos. Hello friends. Today I'm going to give you a quick basic overview to Faraday's laws of electromagnetic induction. Ready? Let's get started. Faraday's laws are the fundamental principle of electromagnetism. It was discovered by Michael Faraday in 1831. So let's imagine we have a coil made of conducting wire, a sensitive galvanometer, and a bar magnet. As seen, the north pole of the bar magnet is towards the coil. So when the magnet is steady, there is no deflection in galvanometer's needle. But when we move the magnet towards the coil, we observe the deflection in the galvanometer. And when the magnet is again steady, there is no deflection in the galvanometer's needle. The flux linked with the coil increases when the magnet approaches near to the coil. Now when we move the magnet away from the coil, there is deflection in the needle in opposite direction. This is due to the flux linked with the coil decreases as the magnet moves away from the coil. The deflection in the galvanometer indicates the production of EMF in the coil. The possible deflection happens when the magnet approaches or withdraws away from the coil. The cause of EMF is a change of flux. The stationary flux cannot induce any EMF in the stationary conductor. Similarly, the same effect can be obtained if we move the coil towards the stationary bar magnet. So, what are the laws of electromagnetic induction? Faraday's first law states that whenever the magnetic flux linked with the circuit changes, an EMF is induced, or whenever the conductor cuts the magnetic field, an EMF is induced in that conductor. The second law states that the magnitude of the induced EMF is equal to the rate of change of flux linkages. To explain it, let us suppose the coil has n number of turns, and let the flux initially be phi1 and the flux at the final point be phi2 in time t seconds. Hence, the flux linkage at the initial point would be n phi1 and at the final point would be n phi2. So the EMF induced will be E is equal to n phi2 minus n phi1 by t, or n in the bracket phi2 minus phi1 divided by t. So the expression in differential form can be written as E is equal to n d phi by dt. Generally, the negative sign is given to the expression to the right hand side. That's because of Lenz law. It states that the direction of the electric current induced in a conductor by a changing magnetic field is such that the magnetic field created by the induced current opposes changes in the initial magnetic field. It is named after physicist Heinrich Lenz, who formulated it in 1834. So the final equation will be E is equal to minus n d phi by dt. Faraday's law isn't just theory. It has real-world application everywhere. For instance, it's the principle behind electric generators. When you spin the coil of the wire within a magnetic field, electricity is produced. This is how we generate power in hydroelectric dams and turbines and even car alternators. Another fascinating application is in transformers. They use Faraday's law to step up and step down voltage levels, making it possible to transmit electricity over long distance efficiently. And induction cooktops in your kitchen. They use electromagnetic induction to directly heat pots and pans, making cooking faster and more energy efficient. So, next time you turn on a light, use your phone, or cook dinner, remember the genius of Michael Faraday and his groundbreaking theory. Thanks for joining me on this quick journey. If you enjoyed this video, don't forget to like, subscribe, and leave a comment below. Stay curious and keep exploring.